Okay, let's start. So we ended up here last time. What are we doing? All semester long, we've been writing what? Net accumulation functions for all kinds of quantities, right? So we did work, we did signed area, we did volume, we did arc length. And basically what we said is if you want to write a function for the accumulation of any quantity, we've got the tools. So what do we need? We have the rate of change function, right? If we have the rate of change function, then we have our basic form of an accumulation function, which involves what major thing? We're going to put the rate into what? Net accumulation function. First thing you think of is it's an integral function, right? It's an integral function. So if we have the rate of change, we can set up this integral net accumulation function based on the rate of change. And we spent the first week of class building that from the ground up. So when we look at an integral net accumulation function, we see all the meaning, right? We're summing up bits of change. Each little bit of change is calculated by m dx, right? M dx. And so then all semester long, we've been practicing setting up accumulation functions, having GC run specific function values for us using function notation, right? This has been our big theme. So now we're talking about this fact that this open form, the net accumulation functions, open form, this thing. Red, this turns out. So, 0 to x, r sub, say it's volume, t dt. And we set up these, maybe this is a volume accumulation function. And we said this open form, it's great for seeing the meaning. It's great for showing us, representing what's going on behind the scenes, but it's not great for computing, right? We need GC to compute values of the dependent variable for us as we plug in x. Okay? And then we saw an example last time where with open form, GC couldn't even do it, right? We needed to solve for something, the spring constant, within the rate function. And not even GC could do that for us. So this motivated the need for what we call closed form. So can we write the same exact net accumulation function? Can we write it in closed form? And so last time we talked about how the way we can do that is through the fundamental theorem of calculus and antiderivatives, right? We laid out how the fundamental theorem of calculus gets another version of this as final minus initial value of the quantity. And then we can get that function, that quantity function, by antiderivative. So we laid all that out. So what are we going to start working on now? Our goal is, given open form net accumulation functions, can we learn techniques for antiderivatives to write those in closed form? Because those are more easily computable. That's the journey we'll be on in the next couple weeks. So we did some easy ones, but then we said the first kind of thing we come to that are harder are undoing the chain rule, right? So if the derivative or the rate function was found using the chain rule, then what about undoing that? So this is a bit more difficult than just the basic rules, right, that you learn on the mastery test. Yeah?
This might sound like a really stupid question, but is there a difference between the integral and the antiderivative?
Yeah. An integral is what we use to, an integral is this. This is an integral. So there's no antiderivative involved in that, right? If we want to write that integral function in closed form, we have to have an antiderivative of that rate function. Does that help? Yeah. So they're very highly, they're related. If we're going to try to write the closed form, then we need an antiderivative of the rate function. But you can have an integral function and it has nothing to do with an antiderivative, right? That's what we've been dealing with all semester. Okay. So then we did these. We said, all right, if we want to be able to undo the chain rule, then we got to know the chain rule really well. So at the end of the class, we did these examples. And so the point was to kind of review the chain rule and also start looking for a pattern so that if we were given something like this, we could recognize that it came from the chain rule and then we can figure out how to kind of undo it and get back the original function whose derivative was the one we were given. So what do all these functions have in common? So if we look at all these rate functions that are results of the chain rule, what is the pattern that we're looking for? What is the pattern that we're looking for to say, oh, that's a chain rule derivative, and I need to kind of recapture the original function because it came from the chain rule. So what's the pattern? So most of the time, how many factors do we have here? How many factors do we have? Meaning how many things multiplied together? 2, right? It's kind of like we always have this first thing and the second thing, right? There's this first and second. Now that's not always the case, but in a lot of times it is. Right? And that first thing was what? Is taking the derivative of the exterior function or the outside function, and what about the inside function? No, I'm still talking about this. So we do the derivative of the exterior, and what about the interior? What happens to the interior when we do the derivative of the exterior? Stays the same. We just leave it as it is. And then, next thing is, second part is the derivative of the interior part, right? So that right there, that's going to be our first kind of check. Can we see that what? If we're seeing maybe this is undoing the chain rule, well, that has to be the derivative or a constant multiple of the derivative of that. And this has to be the derivative or the constant multiple of this interior function, etc. But this might come first, right? So it doesn't have to be in this order when we're given. So this might be first. So is one of them the derivative of the interior function of the other? That's kind of like your check to see if it's undoing the chain rule. Does that make sense? Is one of the factors the derivative of the interior function? If it's not, then it's not undoing the chain rule. Okay, so so we got to recognize this form and then collapse it back together and recover the original function to get our antiderivative. So let's put somewhat of a structure on that. Okay, so let's if that'll work. Okay, here we go. Recall the chain rule says that if you have a function like this, its derivative is. So we're going to do the derivative of the exterior, keeping the interior as it is, times the derivative of the interior. So we got to have that down. We got to know that inside and out, because going backwards is harder. So the better you know it going forwards, the better you'll be able to do it going backwards. Okay? So therefore, this is going to be our form, something like this. Now there may be constants involved, right? Constant multiples. We know with derivative and antiderivative, constant multiples just kind of hang on for the ride, okay? So, but we'll have to work out constants, all right? But this is the general form of working backwards. So, question. What will you focus on in the rate function here on the left in order to recover the amount function? All right, what has the information that we're going to need to recover the amount function? Is it exhibit A or exhibit B? What has the information to recover the original amount or accumulation function? Exhibit A or exhibit B? You should be thinking exhibit A, right? Exhibit B tells us nothing about G. This tells us everything we need. It tells us the derivative of G and F. And so what are we going to do in general? We're going to focus on that and do what? Just one thing to do. What is it? Antiderivative of G, right? Identify the exterior function and do the antiderivative. And what about the interior? Keep it as it is. So that's what going backwards looks like. It means focusing on that to recover that. Okay? Focusing on that. And there's really only one thing to do. Take the antiderivative of G. So we're going to write the antiderivative of the exterior function G, keeping the interior function as it is. Now there's a little mess to clean up with constant multiples. Okay, so that's the only other part, but this is 90% of the ballgame. All right, so what we're going to do is we're going to check it. So we're going to have what we call a first attempt at that antiderivative, and we're going to check it. How do we check it? Take the derivative, right? The whole point of this is we're thinking what function's derivative is the one I'm given. So to check it, we're going to take the derivative. If it's exactly what we started with, then we got it. But it might be off by a constant multiple, and then we adjust. We adjust it, we make a second attempt, and that should do it. Okay, so let's practice. All right, so here's our approach. So first example. All right, so I need to talk about when there's no, so this is a indefinite integral. There's nothing, all semester long we've seen things here and here. Starting value to accumulate from, and final value, right? Which is usually our x. So when there's nothing there, what this means is, it's an indefinite integral. So no limits of integration means it means all possible net accumulation functions, meaning starting from any value of a, right? So no limits of integration means all possible, or the family of, that's a family of functions, all possible net accumulation functions. And how do we get different ones? Depending on what x value we start from. That's when you see it's called an indefinite integral. Indefinite, nothing there. So this means the whole family of functions, net accumulation functions, starting from any value a. That's what that means. Okay, and the reason we don't care about the starting value of a is because we're really focusing on now writing a closed form, right? We want to write a closed form. If we know what the value of x equals a is, it's fine. We actually did a bunch of those. We did some of those last time. So then you just have a particular function that you can write in closed form rather than a general form. Okay, so here we go. So we're going to think of this like g prime f of x f prime of x, the result of a chain rule derivative, and we need to recover the original function g of x. And we said that we need to figure out which part of these, which part is the g prime f of x, right? What I've highlighted in gold on the left. What part is the g prime f of x? So looking at that, what do you think? Do you think it's exhibit A is the g prime f of x, or exhibit B? Exhibit A or exhibit B? You should be thinking it's exhibit B. How can we check? So if it's exhibit B, then what? The derivative of that has to essentially be that. Is it? What is the derivative of 8 plus x to the fourth? 4x cubed. We have x cubed. Is the 4 a problem? No. Constant multiples we can take care of. It needs to have the right exponent, right? So, and it does, right? 4x cubed and x cubed are off by a factor of 4, that doesn't faze us. What would be a problem is if the exponents weren't right? So if this were anything but a 3, we could not do undoing the chain rule. If this were 2 or 5 or 4 or negative something, then it wouldn't work. But we can do this because x cubed is essentially the derivative of x to the fourth, given a multiple. Okay, so what are we going to do? We're going to focus on that and think of that as g prime f. And then we're going to write g of f. So we're going to make an attempt at this by writing what g of f of x would be. So what would it be? The g prime is the exterior function. We're doing antiderivative of the exterior function. What's the exterior function? Something to the fifth power, right? Something to the fifth power. What's the antiderivative of something to the fifth power? That thing to the sixth. So we're going to leave that interior as it is, right? F stays as F, right? F stays as F. And we have to the sixth. Then we also need a 1/6. So that 6 and that 1/6 become 1. So this is our first attempt. This is our first attempt. So we check it. How do we check it? Derivative. So we're going to take the derivative, and we get 6 times 1/6. This is where you got to be, this is all about the chain rule. X to the fourth to the times 4x cubed. And then we ask ourselves, is that exactly the same as the rate function we were given? How is it different? It has an extra multiple of 4. So that extra multiple of 4 tells us how do we adjust the first attempt so that if we checked it again, the 4 would not be there. What else do we need to include with this first attempt so that our check would not have the 4? And then we'll have exactly the rate function. Another 1/4, right? So if we include a 1/4, and if we took the derivative of it, it would work. We'd have it. Now, what did we say the closed form was? The general closed form was final minus initial, right? We said it was the antiderivative, evaluated at x, and then what? Remember? Minus the antiderivative evaluated at a. Remember, it was final minus initial. But with this indefinite integral, a can be anything. So this minus f of a then really becomes a constant, which could change depending on what a is. So depending on what a you start with, you're going to get a constant there. And so rather than write minus f of a, what's customary is to write plus c. Plus c is the same as the minus f of a. That's what the plus c is. So we're going to do what we call the principal antiderivative. That's what we worked on here. And then we have to add c, to account for every possible starting value of a. So we get the whole family of functions. We get the whole family of functions that are the antiderivatives or the net accumulation functions for this rate. So our final answer is going to be 1/24, 8 plus x to the fourth to the sixth plus c. Again, this is the minus f of a part, right? The minus f of a. Okay, so I'm giving you a very systematic kind of method to do this, but the goal is that you can look at this and then write this down. That's where we're heading towards. So the goal is not to memorize these steps, but these steps are supposed to be getting you to think about, we're trying to undo the chain rule. We're looking at this and saying, okay, what function, if I took the derivative of it, would give me this? So that's the goal. You'll get lots of practice and try to keep that in mind. It's like you see this as a chain rule, you're recovering the original function. However you can do that is great. I'm just kind of giving you a systematic approach to get us started, right? Okay, any questions on this example? Next one. Okay, cosine x over sine to the fourth dx. Does this have the form of undoing the chain rule? Looks like a fraction to me. Why? How? If it's a fraction, how does it work? Undoing the chain rule gives you a product, or the chain rule gives you a product of things. How can you rewrite it? Yeah, how can you rewrite it as a product? Yeah, exactly. And this sign to the fourth x is the same thing as this. The whole thing to the minus 4, right? And I think it helps, it makes it easier to see. So this original problem is the same as this problem. Again, now we're asking, does it have this form? Does undoing the chain rule apply? So which is the G prime F? Is it exhibit A or exhibit B? The G prime F? B, right? B. And so how do we check that? We look at the interior of that. Is its derivative the other factor? Is cosine x the derivative of sine? Yes. So we've got the form for undoing the chain rule. Our first attempt is we focus on that term. And we do what? So exterior function is to the minus 4. Antiderivative is to the minus 3. We also need then negative 1/3. So that's our first attempt at the g f of x, right? Take the derivative. Derivative is negative 3 times negative 1/3 sine x to negative 4 times cosine x. Is it exactly the same thing we started with? Is that function exactly the rate function we were given? Exactly the same. Therefore, first attempt was right. First attempt was exactly right. So it's negative 1/3 sine x minus 3 minus f of a, right? Minus f of a, but we just normally put, let's see. If I lost you, please ask. These are the easy ones. Hopefully we can see these. What? All right, so let me, let's see. Okay, how about this one? Another fraction. How can I write it as a product? Six times? Negative 1. Which is the G prime F? Is it the 6 or is it this this thing? Okay, yeah, it's this one. Okay, is the derivative, so to check that, is the derivative of the inside essentially the same as that, right? And all we care about is power, right? Power is what matters. Is the derivative of that, does it have the right power to match with that? Yeah, because the derivative is negative 9. And that's just a constant. Well, 6 is just a constant, so that's right. That's the right power to match up. So now we're going to focus here and do the antiderivative, what? To the negative 1. So you think power, right? So you think, okay, it's 2 minus 9x to the 0 times 1 over 0. And suddenly you get some big warnings that something's wrong because 2 minus 9x to the 0 is 1. All your x's are gone. And 1 over 0 is undefined. Right? There's like warnings all over the place here. Stop, go back, something's wrong here, right? Only Chuck Norris can divide by 0. And my daughter, she can do it. But no one else can. So, so you get all, if you try to do the power rule on something to the negative 1, you get ample warning that you're on the wrong track. X's go away, you get 1 over 0. Danger, Will Robinson, right? So we go back and we say, why didn't power rule work here? What kind of function has a derivative of to the negative 1, or 1 over natural log. So this is the one case where the power rule is it's not really the power rule. This is the natural log rule. The derivative of natural log is to the minus 1 or 1 over. So we start over here. And we do what? We do 2 minus 9x, natural log of it. Okay, and so then there's a domain issue. This is defined for all real numbers except, what, 2/9. But this is only defined for when that thing is positive. Natural log only works with a positive argument. So we need absolute values, so we get the same domain. Absolute value around the natural log gives us the same domain of our rate function and our antiderivative. Okay, so we could have that as a first attempt, or we could look ahead and get it right on the first attempt. What else are we going to need to add here without doing the check and going back and doing a second attempt? What else are we going to need here to make it right? Oh, so we have the 6, right? We can have the 6. So our first attempt, if we wanted, we could do 6 times natural log. Just hold on to the 6. But what else are we? Can we look ahead without manually doing the check and working backwards? Can we see what we're going to need? Also, 1/9? Negative, right? So think about this. When we take the derivative of this, by the chain rule, we're going to have a negative 1/9 multiplied, a negative 1/9 that we don't have over here. Sorry, when we do the derivative, we're going to have negative 9, right? We're going to have an extra negative 9 multiplied by the chain rule. That's a negative 9 we don't have, so we're going to have, we want a negative 1/9. To get rid of that negative 9 that we get from the chain rule, multiplying. So we end up with negative 2/3, natural log, absolute value, 2 minus 9x. Then the minus f of a, we write, plus c. So there's our what? Closed form net accumulation function. What? It gives us the net accumulation of a quantity whose rate is 6 over 2 minus 9x, starting from any value a, right? Starting from any value a, that's the plus c. All right, did I lose you on this one? Please ask if I lost you. Yeah, please.
So, can we use natural log for any fraction?
No, to the negative 1 power only. Like the last one had like sine to the negative 4, I think. That's power rule. The only time natural log comes in is negative 1, because the derivative of natural log is 1 over x, or x to the minus 1. Any other power is the power rule. Any other power is the power rule. Just like the last example. Yeah, please.
So if you did parentheses besides absolute value, would that be incorrect?
In addition to the absolute value or instead of the absolute value?
If you did ln parentheses of 2 minus 9x.
Without the absolute value?
Yeah.
That's not correct. Because that doesn't, this needs to have the same domain as this. If you do just parentheses, then you're restricting the domain. Only when 2 minus 9x is positive will it work. This will always make it positive. And then you match, that matches the domain of this one. Now, if this were something that were always positive as it is, like x squared plus 3, you know, like if it's ln of x squared plus 3, well, that's always positive anyway. That's never negative. So you wouldn't need the absolute value. But you can always put it on. It won't be wrong to put it on. So just make it a habit to put it on. All right. Okay, next one. Okay, this one a little bit tricky. I'm going to start attendance, see if you can work on this. But you got to be good to get this. This is a little tricky, but it is undoing the chain rule, so give it a shot. So, what is the G prime F? Exhibit A or Exhibit B? So, which one has, as its derivative, the other factor, right? So, on the inside. Where do we see a derivative? Is tan minus x the derivative, or is 1 over 1 plus x squared the derivative? That's the derivative, right, of that. So that must be the f prime x, and that must be the g prime f. That must be the one we're focusing on. So, So we need to see this as a composite function, g prime of f, and then do the antiderivative of g. How do we do that? Anyone figure it out? How do we see that tan inverse x as g prime of x and do the antiderivative of g? Anyone think they got it? Yeah.
That may be obviously wrong, but so I got 1/2 10 to the negative 1x squared.
So you saw this, so what did you see this? That's right. So you saw this as what? Tan minus x. What did you see the g prime function as?
I wrote it like backwards.
Yeah, you did it.
I got 10 to the, so if I just use 10 to the negative 1, then I have to divide it by 1 plus x squared, and I was missing 1 10 to the negative 1 as a numerator. So I had to add, so I have to square it to get 2 of them, and that's divided by 1/2.
Okay, so you got the right place in the end, but how you got there, I don't think was. But so sometimes lucky is good. Anyone, how can we explain this tangent to the negative 1x as? Yeah, Brian.
Is it not the same as like if you tangent to the negative 1 of x, like in parentheses squared, or to the first power?
To the first power.
And then using the power rule, you just add 1, and then it becomes that to the second power over 2.
That's it. That's it. So you have to see this as that whole thing to the first power rule, so that our g prime function, this exterior function, is something to the first. So it's tricky. But now that you've seen it, you can be on the lookout for it, okay? So the first attempt is, we're going to raise power, right? Tangent inverse x to the second. But then we also need 1/2. If you take the derivative of that, do you get exactly what you started with? Yes. If you take the derivative of this, you get exactly what we started with. We're done. Okay, for those who have done this before, you probably learned something called U substitution to do these. We're going to do U substitution later on for ones that can't be done this way. But the reason I recommend this is 2 reasons. When you get good at this, it takes about 1/3 or 1/4 of the time and writing. U substitution is much longer. It takes much longer. People feel very comfortable with it, but in the long run, you're doing a lot more work. Okay? If you once you improve at this method of just kind of looking at these and being like, okay, what function, if I did the chain rule, would have this derivative? Okay, 1/2, so kind of what we're getting at. So that's the first reason. This is a lot quicker and more efficient than U substitution for doing these. The other reason is, again, we're focusing on thinking about derivative rules backwards. U substitution is like learning a whole new method. It's like learning a whole new method. If we already know the chain rule, let's use it and just try to think in reverse doing chain rule. That's what this is focused on. So I highly, if U substitution, it feels like a security blanket, I highly recommend learning this for efficiency and for focusing on derivatives, not learning a whole new set of rules, but just taking from the derivative rules we already know and doing them backwards. Okay? All right, questions on this one? All right, so let's do, is there one more on this list here? No, that was the last one. Good. All right, let's look at this example. So culture, so now we're going to apply this. We're going to apply this to rate of change and accumulation. So a culture bacteria in a particular dish has an initial population of 250 cells and grows at this rate, 50 e to the 0.3 t. So I want to write two expressions for the population t days after the initial measurement. One of those functions, we write that p function in open form, and then in fully simplifies closed form. So open form is what we've been working on the past month, all semester. And now we have this way of rewriting, starting to rewrite these net accumulation functions in a closed form. So then we're going to apply that. So take a minute and see how far you get. I want to make sure we finish this example. Yeah. So take 2 minutes. See. So most of you got the open form. Here's the open form. Everyone check your open form. So remember, this is our total amount function, right? Everything that you had before plus accumulating bit by bit starting from our A value, right? And our A value is going to be 0 because t is like number of days since the initial measurement, right? So we want t to be number of days, so then we're going to start from 0. And then you can use any letter you want besides t, right? I used U, okay? So that's what we've been doing all semester. That's review. Okay, and so now we can do a closed form by what? Seeing what function has this as its derivative. What function has this as its derivative? So is it undoing the chain rule? We have e to the 0.3u, right? So the interior function, this is like the g prime f. The interior function is 0.3u. Is its derivative, the interior function, the same power as that? Yes, right? The derivative of 0.3u is something to the 0th power, and that's what 50 is. So we need to do the antiderivative of e to the something. What's the antiderivative of e to the something? Just e to the something, right? That's the function whose derivative is the same as its original function. So the antiderivative of e to the 0.3u is e to the 0.3u. But then we need a 1 over 0.3, right? We need a 1 over 0.3, and the 50 comes along for the ride. So I'll let you stare at that, the antiderivative of that rate right there, and ask me if I lost you. The 50 over 0.3 e to the 0.3u. Does it make sense? Can you get that? It's like an easy-ish undoing the chain rule. Now this notation means what? Final minus initial. Plug in t, so f of t minus f of 0. That's what this notation means. Plug in t, plug in 0, and subtract. So that's our f of t minus f of a, or f of 0 in this case.
Do you want that notation for the line T0?
What's it?
Do you want that notation for the homework with the line T0?
It's just helpful to split it up into steps. It's not like worth points or anything. It's just helpful. Okay, so so then we plug in t, plug in 0, and subtract. So this is our f of t minus f of 0. But we still have the plus 250. Okay, now, may I have your attention, please? Don't miss this. Just because a equals 0 doesn't mean that f of a equals 0. I'll say it again. Just because a equals 0 doesn't mean f of a equals 0. Case in point. Is this 0? No. And the past 2 semesters, about 80% of the class has missed the question on the test because of this. They just write this down and they say, that's it. There's my function. And they tack on the plus 250. But what happens here? What is this? Right, this is negative something, right? This is not a non-zero value. So what do we get? Ah, shoot. I should have done it in 2 steps. What is this? This is minus. This is 1. So you get equals 250 plus function minus 50 over 0.3. This does not go away. It's not 0. Just because you start at a equals 0 doesn't mean f of a is 0. Cosine is another example. Cosine of 0 is not 0, right? So now these are both constants. We can join these together. We can take 250 minus 50 over 0.3 and simplify that. And we get this part, 50 over 0.3 e to the 3t, plus 83.3, not plus 250. Yeah?
So to repeat the statement, just because your a is equal to 0 doesn't mean your f of a.
That's right. That's right. When we do this, this is going to be what? F of t minus f of a. Or this thing of t, and that's your f right there. That's your f. That's your antiderivative. This is f of t minus f of a. Just because a is 0 doesn't mean f of a is 0. You've got to chase that out. More of you are going to get it right on the test this time. Please. Not only 20% of you, okay? So we got to combine that minus f of a with the initial 250. That gives you the 83.3. That's the closed form. So now if you want to find, you can pack up, but just listen. If you want to find the population 10 days after the initial measurement, what are you going to use? Are you going to use the open form or are you going to use the closed form? Closed, right? It's beautiful. It's easy. Plug in 10.